Good morning. Today's course will be about a method of computing a basis for a linear, homogeneous, ordinary differential equation called the auxiliary polynomial. This method only works for equations with constant coefficients, however. So to go over what we did last time again, a linear differential operator is an expression where you have a sum of coefficients which can be functions of x times derivatives. So for example, an of x times d to the n. Here, d means the derivative is a function of x, d over dx. So this is an operator that gets applied to a function, and the output is another function. And the coefficients of the operator are an of x, an minus 1 of x, up to a0 of x. And when these coefficients are constant, this will lead to an equation with constant coefficients. Any linear equation can be written in the form a linear operator, a linear ordinary differential operator like t applied to the unknown function y is equal to the source term f. If f is non-zero, the equation is called inhomogeneous. If f is 0, which is the case we are studying now, then the equation is called homogeneous. So a homogeneous equation is ty is equal to 0, where t is some differential operator, some linear differential operator. If the equation is homogeneous, then solutions to a homogeneous linear equation always form a vector space, and the dimension of the vector space is always equal to the order of the equation. So if we know the dimension of the vector space, it is enough to find a basis for the vector space, and we can express every solution as a combination of the solutions in the basis. However, in general, a basis may not be easy to find, but for homogeneous linear equations with constant coefficients, there is a universal method, namely the auxiliary polynomial. All right, so here is one more example. Let's consider the equation y double prime minus e to the x plus x times y is equal to 0. This is a linear second order ordinary differential equation. It is homogeneous because we have 0 on the right hand side. And so I mean, not only do we have 0 on the right hand side, but there is no term which is only a function of x. So we have y double prime, and then the next term y prime is missing, and then minus e to the x plus x times y. So this is the term that contains y, and minus e to the x plus x is the coefficient of y. So notice that it is an equation with non-constant coefficients. However, since this is a linear homogeneous equation, solutions form a vector space, and because this is a second order equation, it will be a vector space of dimension 2. So this means that if we find two linearly independent solutions for this equation, then they will form a basis and every solution can be expressed as a linear combination of these two solutions. However, for this equation, it may be hard to find a basis. Actually, it may be hard to find any non-zero solution by an explicit formula. Probably the best we can do is to find a solution by means of a power series or numerically. So this equation is sufficiently complicated that we may be unable to find the explicit formula for a solution. However, if we are able to compute two linearly independent solutions, let's say numerically, then we'll know that every other solution is a linear combination of those two solutions. By contrast, let's consider an equation with constant coefficients, and we're going to analyze it in depth. So this is a simple equation, y double prime plus 4y is equal to 0. This is a second order linear ordinary differential equation. It is homogeneous, so there are no terms that contain just the variable x. So when we have 0 on the right hand side, and it has constant coefficients, so the coefficient of y double prime is 1, y prime is missing, so we can say it has the coefficient 0, and y has the coefficient 4. So this is an equation with constant coefficients, and we're going to see very soon it is easy to find its basis. For now, let me just state that the standard basis for this equation is made of the two functions sine of 2x and cosine of 2x. So for now, it doesn't matter how I got this basis. Let us check that it really is a basis. So we have to check several things. First of all, that the two functions sine of 2x and cosine of 2x are solutions of the equation, because we are looking for a basis for the space of solutions. So we want two functions which are solutions. So, well, let's check. The second derivative of sine of 2x is minus 4 sine of 2x. And the second derivative of cosine of 2x is minus 4 cosine of 2x. So let's check. The derivative of cosine of 2x is minus 2 sine of 2x. And when I take one more derivative, we get minus 4 cosine of 2x, where the factors of 2 come from the chain rule. So every time we take a derivative, the 2 in 2x gets brought out by taking the derivative. So, okay, so we check that these are solutions, and then there are two of them, and we want there to be two functions in the basis, so this is appropriate. And then it is enough to check, if we have two functions, it is enough to check that their Wronskian is non-zero. So in this case, the Wronskian of sine of 2x and cosine of 2x is minus 4, which is always non-zero. So they really form a basis. And I'll let you check by using a determinant that the Wronskian really is minus 4. So regardless of how we got these two functions, they really form a basis for the space of solutions for this equation. And therefore, every solution to the equation can be written as a linear combination of these two solutions. So the general solution to the equation is some constant C1 times sine of 2x plus another constant C2 times cosine of 2x. So by finding two linearly independent solutions to the equation, actually we have found out all the solutions to this equation. Okay. In addition to this standard basis made of sine of 2x and cosine of 2x, turns out there is another standard basis for this equation made of e to the power 2ix and e to the power minus 2ix. So this is the exponential of a complex number because I here is the imaginary unit. So I square is minus 1. So I is a complex number. So again, let's check that these two functions form a basis. Well, every time we take a derivative of an exponential, so the derivative of e to the power ax is always a e to the power ax. So taking the derivative brings a factor of a out by the chain rule. So taking the derivative of e to the 2ix gives 2I e to the 2ix. So it brought the 2I out. And then taking the second derivative brings another factor of 2I. So we get 2I squared e to the 2ix. But 2I squared is the same as 4I squared, and I squared is minus 1. So we get minus 4 e to the 2ix. So it really is a solution of the equation because e to the 2ix double prime plus 4 e to the 2ix is equal to 0. So it really fulfills the equation. And same for the other one, if we had e to the minus 2ix, well, I'll let you check that it fulfills the equation for the same reason. Because minus 2I quantity squared is also equal to minus 4. Okay, so these are solutions. Next, there are two of them, which is as many functions as we would want in a basis, because this is, again, a second order equation. And finally, we need to check that they are linearly independent. So for an n-dimensional vector space, n functions or n elements form a basis if they are linearly independent. And in our case, linear independence is checked by using the Wronskian. So the Wronskian of e to the 2ix and e to the minus 2ix is minus 4i. And again, you can check this, and you should by using a determinant. All right, so we have two functions. They are linearly independent, so they also form a basis for the space of solutions. This means that every solution to this ordinary differential equation can also be written as a combination of these two solutions. So the general solution is y of x is equal to c1 tilde e to the 2ix plus c2 tilde e to the minus 2ix, where I denoted them by c1 tilde and c2 tilde because they are not the same as the constants c1 and c2 from the previous page. So every solution can be written both as c1 times sine of 2x plus c2 cosine of 2x, and as c1 tilde e to the 2ix plus c2 tilde e to the minus 2ix. So two different ways of writing the general solution to this equation. it is clear that there should be a relation between the two ways of writing the solutions, and we'll look at it on the next page. So in order to understand how to go from one formula to another, let's have another look at the exponential of a complex number. The exponential of a complex number can be defined in the same way as the exponential of a real number by a power series. So one of the usual ways of defining this exponential is by the power series 1 plus z squared over 2 factorial plus z cubed over 3 factorial plus z to the 4th over 4 factorial plus z to the 5th over 5 factorial, so etc. This is an infinite sum. And so again, exponential z, or e to the z, is equal to this sum, and this sum is guaranteed to converge. So this infinite sum is guaranteed to converge for every real and every complex number z. So for complex numbers as well, this exponential has the usual properties. E raised to the power a plus b is equal to e to the a times e to the b, and e to the 0 is equal to 1. So this can be used to reduce the exponential of a complex number to more familiar functions. Every complex number is the sum of its real part and its imaginary parts. So let z be a complex number, and then it can be written as a plus ib, where a is the real part and it's a real number, and ib is the imaginary part. So I is the imaginary unit, and b is a real number again. Then e to the z is e to the a plus ib, which is e to the a times e to the ib. E to the a is just the exponential of the real number a, and let's see on the next page that e to the ib is equal to cosine b plus I sine b. So again, this is proved by comparing power series, or at least this is one way of proving it. We plug IB in the power series that defines e to the IB, and we get 1 plus IB squared over 2 factorial plus IB cubed over 3 factorial plus IB to the 4th over 4 factorial plus IB to the 5th over 5 factorial, etc. And in each of these terms, we factor separately the power of I. So I being the imaginary unit, so we have 1 plus IB plus I squared b squared over 2 factorial plus I cubed b cubed over 3 factorial plus I to the 4th b to the 4th over 4 factorial, etc. And since the imaginary unit has the property that I squared is minus 1, this means if we multiply by I, means that I cubed is minus I, and then if we multiply by I again, I to the 4th is minus I squared, which is 1. So from this point forward, starting with I to the 4th, which is 1, the powers begin repeating. So the next power is I to the 5th, which is I, and then I to the 6th will be the same as I squared again, which will be minus 1, etc. And then we see that these powers repeat themselves. So there is a certain pattern, there's a certain periodicity to the powers of I. They repeat once every 4 powers. And then if we also group the powers that turn out to be real numbers, so first power is 1, the third power is minus 1, The fifth power is 1 again, etc. So we get 1 minus b squared over 2 factorial plus b to the 4th over 4 factorial minus b to the 6th over 6 factorial, etc. And then we also separately group the powers that still contain I, and we get I times b minus b cubed over 3 factorial plus b to the 5th over 5 factorial plus, and then the next one should be actually minus b to the 7th over 7 factorial, etc. Then the first group is just the power series of cosine of b, and the second group is I times the power series of sine of b. So indeed, by comparing the power series, e to the ib is cosine b plus I sine b. This relation is called Euler's formula. E to the I theta is cosine theta plus I sine theta. And this goes both ways. We can compute e to the I theta in terms of cosine theta and sine theta. And we can also compute sine and cosine in terms of complex exponentials. So the way we do that is, in addition to having e to the I theta, we also compute e to the minus I theta. So we plug in minus theta instead of theta. And then we get, this is cosine of minus theta plus I sine of minus theta. So cosine is an even function. So cosine of minus theta is equal to cosine of theta. And then sine is an odd function. So sine of minus theta is minus sine theta. So e to the minus I theta is cosine theta minus I sine theta. So we have two relations now. E to the I theta is cosine theta plus I sine theta, and e to the minus I theta is cosine theta minus I sine theta. And then we can add them and divide by 2, and we get that cosine theta is e to the I theta plus e to the minus I theta over 2. And if we subtract them, we get that sine theta is e to the I theta minus e to the minus I theta over 2i. So either way, we actually have at least 3 relations. E to the I theta is cosine theta plus I sine theta, and then 2 more relations that express sine and cosine in terms of complex exponentials. Sine theta is e to the I theta minus e to the minus I theta over 2i, and cosine theta is e to the I theta plus e to the minus I theta over 2. These relations are called Euler's formulas. And out of all of these, probably the most interesting and surprising case is when you set theta to be pi. So then you get e to the I pi is equal to cosine of pi plus I sine of pi. So it's equal to minus 1. So e to the I theta, e to the I pi is equal to minus 1. So now that we have these formulas for the complex exponential and for sines and cosines, let's go back to our 2 ways of writing the general solution for the equation. So on one hand, we can write the general solution as c1 sine of 2x plus c2 cosine of 2x. And on the other hand, with a different pair of constants, you can write it as c1 tilde e to the 2ix plus c2 tilde e to the minus 2ix. So let's try to compute one pair of constants as a function of the other. So let's write e to the 2ix as a function of sine and cosine. So e to the 2ix from Euler's formula is cosine of 2x plus I sine of 2x. And e to the minus 2ix, which is also part of our solution, is cosine of 2x minus I sine of 2x. So making this substitution, we get that y of x is equal to c1 tilde times, and I replaced e to the 2ix by cosine of 2x plus I sine of 2x. And it's plus c2 tilde times, and I replaced e to the minus 2ix by cosine of 2x minus I sine of 2x. And then let's write this in terms of sine and cosine. So factoring cosine of 2x, you get c1 tilde plus c2 tilde times cosine of 2x. And then plus I c1 tilde minus I c2 tilde times sine of 2x. So on the other hand, the representation of the solution in each basis is unique. So every solution can be written in a unique way in each basis. And we had already written the solution as c1 sine of 2x plus c2 cosine of 2x. So this means that the coefficients in front of sine and cosine must be the same. So c1 tilde plus c2 tilde must be equal to c2, which is the coefficient of cosine, and I c1 tilde minus I c2 tilde must be equal to c1, which is the coefficient of sine. So we obtain the relation between the coefficients used to write y of x in one of the bases and the coefficients used to write y of x in the other bases. So each and every solution can be written either way, either as a combination of sines and cosines, or as a combination of complex exponentials for this equation. In each basis, the coefficients are unique, and there are relations between them which tell us how to go from one representation to another. So knowing C1 and C2, one can compute C1 tilde and C2 tilde, and conversely, knowing C1 tilde and C2 tilde, one can compute C1 and C2. Our method using the auxiliary polynomial may lead us to use complex exponentials, but then it's always more natural, or at least it feels more natural, to go from those complex exponentials to sines and cosines, as we'll see next in the course. So this is the method of the auxiliary polynomial. Now let's try to use it to solve linear equations with constant coefficients. This is the general form of a homogeneous linear ordinary differential equation with constant coefficients. So we have an times the nth derivative of y plus an minus 1 times the n minus 1th derivative of y plus plus a2 times the second derivative of y plus a1 times y prime plus a0 times y is equal to 0. And what matters here is that an minus 1 all the way up to a0 are constants. So this is an equation with constant coefficients. They are not functions. Okay, so in that case, let's consider the auxiliary polynomial. What is the auxiliary polynomial? It is the polynomial that we get by replacing each derivative of y with a power of some variable lambda. So we replace the nth derivative of y with the nth power of lambda. So we replace every derivative of y with the same power of lambda. So we get if the equation had order n, we get a polynomial of degree n. So, and the coefficients are the same. So I get an lambda to the n plus an minus 1 lambda to the n minus 1 plus etc. all the way down to a0. So a0 is the coefficient of y with no derivatives. So then in the polynomial, a0 is multiplied by lambda to the power 0, which is 1. So a0 is the term with no power of lambda. Right? Then this leads us directly to solutions of the equation. If lambda is a solution of the auxiliary polynomial, so p of lambda is equal to 0, then e to the lambda x is a solution of the ordinary differential equation. So for each root lambda of the auxiliary polynomial, we get an exponential solution of the ordinary differential equation. Right, here is a proof. So let's say this is the auxiliary polynomial, an lambda to the n plus an minus 1 lambda to the n minus 1 plus etc. plus a1 lambda plus a0. All right, then we want to show that e to the lambda x is a solution of the ordinary differential equation if p of lambda is 0. So let's plug e to the lambda x in the ordinary differential equation. So we set y is equal to e to the lambda x in the equation in the previous page. So in this equation, we set y is equal to e to the lambda x. All right, so then applying all the derivatives in the equation to e to the lambda x, then we see that the first derivative of e to the lambda x is lambda e to the lambda x. The second derivative of e to the lambda x then is lambda squared e to the lambda x. So each derivative brings down one more factor of lambda. So in general, the nth derivative of e to the lambda x is lambda to the n e to the lambda x. For example, the 10th derivative of e to the lambda x should be lambda to the 10 e to the lambda x. So then when we apply this differential operator to e to the lambda x, then each d to the n, so each derivative of order n produces a lambda to the n. So d to the n produces lambda to the n, d to the n minus 1 produces lambda to the n minus 1, times e to the lambda x, etc. And for example, the last one is a1 times the derivative of e to the lambda x, and this becomes a1 times lambda e to the lambda x. And then we have plus a0 e to the lambda x, because a0 is times y with no derivative. And then we factor e to the lambda x from everything. And we get an lambda to the n plus an minus 1 lambda to the n minus 1 plus etc. all the way to a0 times e to the lambda x. But this expression is nothing but the auxiliary polynomial. So an lambda to the n plus an minus 1 lambda to the n minus 1 plus etc. all the way to a0 is the auxiliary polynomial applied to lambda. So then if p of lambda is 0, if the auxiliary polynomial applied to lambda is 0, then this whole expression becomes 0. So indeed, if lambda is a root of the auxiliary polynomial, then e to the lambda x is a solution of the equation. All right. So if the auxiliary polynomial has now n distinct roots, so being a polynomial of degree n, it could have up to n distinct roots, but it could also have fewer than n distinct roots if some roots repeat. So now if it has n distinct roots, it turns out that these roots give rise to a basis for the space of solutions. So if lambda 1 up to lambda n are the roots, then e to the lambda 1x up to e to the lambda nx are all solutions, and they are all linearly independent, and they form a basis for the space of solutions. So in order to check that they form a basis, we need to check two things. First, are there n of them? So again, if the polynomial has n distinct roots, where n is the order of the equation, and it's also the degree of the polynomial, then yes, there are n of them. And second, we need to check whether these exponentials are linearly independent. And for that, we compute their Wronskian. And computation, which I'm not going to do here, shows that their Wronskian is indeed always non-zero. So it's equal to e to the sum of lambda 1 up to lambda n times x, and then times the product of all the differences between the roots. So product of lambda k minus lambda j over all values of j and k, all distinct values of j and k between 1 and n. So then if all the roots are distinct, then this product is non-zero, and then the Wronskian is non-zero, and then these exponentials form a basis. So let's see an example of how this works for a concrete equation. Let's consider the equation y triple prime minus 3y double prime plus 2y prime is equal to 0. This is a linear homogeneous third order ordinary differential equation. So when computing the auxiliary polynomial, we replace each derivative by a power of lambda. So y triple prime becomes lambda cubed, and then minus 3y double prime becomes minus 3 lambda squared. So second derivative of y is replaced by lambda squared, and then plus 2y prime becomes plus 2 lambda. So one derivative of y is replaced by 1 power of lambda. And then if there were an extra term, like let's say plus 7y, then we'd have an extra term like plus 7 in the auxiliary polynomial. So the terms that contain just y become terms that contain no power of lambda, or lambda to the 0. So in our case, the polynomial is lambda cubed minus 3 lambda squared plus 2 lambda. And we want to find out its roots and see if they're all distinct. So if it has 3 distinct roots. And well, so we start with lambda cubed minus 3 lambda squared plus 2 lambda. We factor a lambda. And then we get that this is lambda times lambda squared minus 3 lambda plus 2. And this can also be factored by solving the quadratic equation or whatever method you want to use. And So it factors overall into lambda times lambda minus 1 times lambda minus 2. And then when we set this equal to 0, this means that either lambda is 0, or lambda minus 1 is 0, or lambda minus 2 is 0. So the three roots are 0, 1, and 2. So these really are three distinct roots, so 0, 1, and 2. There's no repetition on the list. And therefore, well, so there are three of them, three distinct roots. So basis for the space of solutions consists of these three exponentials, e to the 0 times x, e to the 1 times x, and e to the 2 times x. Or in other words, e to the 0 times x is 1, e to the 1 times x is e to the x. So we got the basis made of the three functions, 1, e to the x, and e to the 2x. So every solution to the equation can be written as a combination of these three basis solutions. So the general solution to the equation is some constant c1 times 1 plus some other constant c2 times e to the x plus some other constant c3 times e to the 2x. So the general solution is c1 plus c2 e to the x plus c3 e to the 2x. And so this is the general solution. This is a solution for any three real numbers, c1, c2, c3. And any solution can be written in this form. So this is the general solution of the equation. And it contains three constants, which is expected because this is a third order equation. If we want to find a particular solution, then we should solve an initial value problem consisting of this equation with three initial conditions. And then knowing the three initial conditions will give us the three constants C1, C2, and C3 after some computation. Okay, now let's consider an example where we have complex roots. So let's consider the equation y double prime minus 2y prime plus 8y is equal to 0. So then this is again a linear second order ordinary differential equation, and it is homogeneous. So it can be solved by the method of the auxiliary polynomial. And so let's see what the auxiliary polynomial is. We replace y double prime by lambda squared. We replace minus 2y prime by minus 2 lambda. And we replace 8y by x. So please remember, y with no derivative gets converted to lambda to the 0, which is 1. So this is why we have 8 with no power of lambda. Okay, so we want to find the roots of this polynomial, and to do that we solve the quadratic equation lambda squared minus 2 lambda plus 8 is equal to 0. This has two solutions. Let's check. So you should use the quadratic formula if you want to solve this equation, and the two roots are 1 plus or minus square root of minus 7. And square root of minus 7 is the same as square root of minus 1 times square root of 7. So it is plus or minus I times square root of 7. So the two solutions are 1 minus I square root of 7 and 1 plus I square root of 7. Right. So then we see that these really are two distinct roots again. 1 minus I square root of 7 and 1 plus I square root of 7. And then a basis for the space of solutions is given by these exponentials, e to the 1 minus I square root of 7 times x, and e to the 1 plus I square root of 7 times x. So you can see that using the auxiliary polynomial very naturally leads to solutions given by complex exponentials. So every solution can be written as a combination of these two solutions. So it's some constant C1 times e to the 1 minus I square root of 7 times x, plus another constant C2 times e to the 1 plus I square root of 7 times x. So again, notice that by finding out two solutions, we have actually found out the general solution to the equation. Well, this is because these two solutions are linearly independent. However, instead of writing the solutions in terms of complex exponentials, many people prefer to get rid of the complex exponentials and write it in terms of exponentials, sines, and cosines. So we can always do something like this when the equation has real coefficients. It turns out that when the equation has real coefficients, the auxiliary polynomial, which has the same coefficients, then also has real coefficients. And then if a polynomial has real coefficients, then any non-real roots, like here, 1 minus I square root of 7 and 1 plus I square root of 7, must come in conjugate pairs. So, for example, for us here, 1 minus I square root of 7 and 1 plus I square root of 7 are a pair of conjugate roots. And in general, the conjugate of a complex number a plus ib, where a and b are real numbers, is denoted by z with a bar on top, which is read z conjugate, or z bar, and which is equal to a minus ib. So for example, the conjugate of 2 plus 3i is 2 minus 3i. The conjugate of 1 plus 10i is 1 minus 10i. And for the equations that we're solving, the non-real roots will always come in pairs of conjugate roots. So what we're going to do for this equation will be applicable for other equations as well. So for each pair of conjugate roots, let's say u plus iv and u minus iv, where u and v are real numbers, we're going to have a pair of complex exponentials in our basis of solutions. So e to the u plus iv x and u to the e to the u minus iv x. And then, as I say here on this slide, they can always be replaced in the basis by the pair e to the ux cosine of vx and e to the ux sine of vx. So here are the formulas that can be used in changing the basis from one pair to another. So e to the u plus or minus ivx is e to the ux cosine of vx plus or minus I e to the ux sine of vx. So each of the two complex exponentials can be represented as a combination of e times cosine and e times sine. And conversely, each of these two exponentials times sine and cosine can be written in terms of complex exponentials. So for example, e to the ux cosine of vx is equal to the sum of the two complex exponentials divided by 2. And e to the ux sine of vx is equal to the difference of the complex exponentials divided by 2i. So they are interchangeable. So in our example, we had a pair of complex roots, 1 plus I square root of 7 and 1 minus I square root of 7. So this means that we can replace the complex exponentials e to the 1 plus I square root of 7 times x and e to the 1 minus I square root of 7 times x by this pair here. So the real part was 1 and the complex and the imaginary part was I square root of 7. So another basis for the space of solutions is e to the x cosine of square root of 7 times x and e to the x sine of square root of 7 times x. So when we have this pair of roots, 1 plus or minus I square root of 7, this gives rise to a pair of real solutions which can replace the complex exponentials, and it's e to the 1 times x cosine of square root of 7 times x and e to the 1 times x times sine of square root of 7 times x. So this means that instead of using complex exponentials, we can write any solution in terms of these functions. So any solution y of x is equal to some constant c1 tilde times e to the x cosine of square root of 7 times x plus another constant c2 tilde e to the x sine of square root of 7 times x. Okay, and the constants c1 tilde and c2 tilde are not the same as those in the previous representation of the general solution. So here we have c1 and c2 times these complex exponentials. And again, there exists a very direct relation between c1 and c2 on one hand, and c1 tilde and c2 tilde on the other hand. Right, so this way of rewriting the solution only applies to complex roots. There is nothing we need to do about real roots. For real roots, the corresponding solutions in the basis are given by exponentials, just real exponentials, no sines and cosines. And doing this replacement, so eliminating the complex exponentials from the basis and replacing them by a combination of real exponential sine and cosine is preferred by many people because they like dealing with real solutions instead of complex exponentials. All right, so now let's consider the equation. Another example, y triple prime minus y is equal to 0. The auxiliary polynomial in this case is lambda cubed minus 1 because y triple prime becomes lambda cubed and minus y becomes minus 1 in the auxiliary polynomial. So notice again, please be careful with this, that y having no derivatives becomes not lambda but 1. So y becomes 1. So let's find the roots of this polynomial. Let's solve the equation lambda cubed minus 1 is equal to 0. And again, in order to find it, we need to factor the polynomial. It's clear that 1 is a root. I mean, we can see by plugging in lambda equal 1. 1 cubed is 1 minus 1, that's 0. So then we should factor the polynomial, and we get that lambda cubed minus 1 is equal to lambda minus 1 times lambda squared plus lambda plus 1. So one of the roots was lambda is equal to 1, and the other two roots, in order to compute them, we should solve the quadratic equation lambda squared plus lambda plus 1 is equal to 0. So the other two roots turn out to be, well, please check by solving the quadratic equation yourselves. So they turn out to be minus 1 plus or minus square root of minus 3 over 2. And square root of minus 3 is plus or minus I square root of 3. So you get minus 1 plus or minus I square root of 3 over 2. Right, so we have three roots now. 1 minus I square root of 3 over 2, and minus 1 plus I square root of 3 over 2. So a basis for the space of solutions is given by these three exponentials, one of which is a real exponential, e to the 1 times x, which is the same as e to the x, and then the other two being complex exponentials, so e to the minus 1 minus I square root of 3 over 2x, and e to the minus 1 plus I square root of 3 over 2x. And it's better to split the fraction, so minus 1 minus I square root of 3 over 2 is the same as minus 1/2 minus I square root of 3 over 2, and minus 1 plus I square root of 3 over 2 is minus 1/2 plus I square root of 3 over 2. So this is then the general solution of the equation. It's a combination of these three solutions. So it's some constant times e to the x plus another constant times the first complex exponential plus another constant times the second complex exponential. So now, remembering that we would like to replace the complex exponentials by real exponentials, cosines, and sines, then for each pair of conjugate roots, e to the u plus avx and e to the u minus avx, we want to replace it by e to the ux cosine of vx and e to the ux sine of vx. So this is why we wrote the roots like this. Now it is clear that they are conjugates, so they are minus 1/2 minus I square root of 3 over 2 and minus 1/2 plus I square root of 3 over 2. So u, the real part, is minus 1/2, and v, or the imaginary part, is square root of 3 over 2. So the real part gives rise to a real exponential, and the imaginary part gives rise to sines and cosines. So we can replace those complex exponentials in the basis by the pair made of e to the minus x over 2 cosine of x square root of 3 over 2 and e to the minus x over 2 sine of x square root of 3 over 2. So this means that our new basis, which is obtained by replacing the complex exponentials by these functions, is made of e to the x, e to the minus x over 2 cosine of x square root of 3 over 2, and e to the minus x over 2 sine of square root of 3, sine of x square root of 3 over 2. Then, since this is again a basis, every solution of the equation can be written as a combination of these three special solutions. So it's some constant times e to the x plus another constant times e to the minus x over 2 cosine of x squared to 3 over 2 plus another constant times e to the minus x over 2 times sine of x squared to 3 over 2. And the constant C1, which is the coefficient of e to the x, actually turns out, if you do the computations, turns out to be the same as the constant C1 in the other representation. So C1 is actually the same. And the other two constants, of course, get changed. All right? So then this means that now we know how to solve linear homogeneous equations by the method of the auxiliary polynomial when all the roots of the auxiliary polynomial are distinct. And we have looked at the case when the roots are real, and as also at the case when the roots are complex numbers. And next time, we'll look at the case when not all the roots are distinct. So this is another possibility that we need to consider, that the polynomial has roots of multiplicity. For example, 2 of its roots are 3, and another one is 1. All right, so we'll look at these possibilities in the next course. Thank you for your attention.